Good afternoon. This is Dr. James Gerald with the Department of Chemistry and Physics here at Delta State University. And here today, we're going to start talking a little bit about remote sensing. In particular, we're going to talk about the optical spectrum. And we're going to start with talking about the human eye. And the reason we're going to talk about the human eye is there are a number of things about the human eye, which is the remote sensing tool you're the most familiar with. There are a number of things about the human eye that and things that can go wrong with it and how it works that are common across all remote sensing technologies. First, the human eye, it has, the cornea, it has your lens, vitreous humor. This is where you see all those little things floating around in bright light. There's the fovea and the retina, which sits right here on top of the fovea. The retina is where all of the, if you will, all of the imaging action takes place. The lens, light comes in through the lens. The lens focuses, if you're in good luck, the lens focuses that image onto the retina. There's also the optic nerve coming out of that. The optic nerve creates a blind spot that you normally don't see because we have two eyes, and that blind spot is in different locations of your field of vision. And so you use your left eye to fill in the blind spot on your right eye, and use your right eye to fill in the blind spot on your left. Now, this will bring up something you're not accustomed to really thinking about. Your brain is processing two images into one because there's an image on your left eye, there's an image on your right eye. The two images together give you the information that your brain uses to create internally what we call the image we're seeing. There's a simple lens equation for the physics of the eye, which is the power of the eye. This P here, power of the eye, is 1 over the focal length. Now, if you really want to know more about that, you should show up on campus one semester and take geometric and visual optics, where we'll talk about how your glasses work and things that go wrong with the eye and how we adjust all of that. But for the most part, this lens equation, it's the same one we use for cameras, it's the same one we use for telescopes, it's the same one you use when you try and focus the sun using a magnifying glass and burn ants on an ant hill. You're actually making use of this equation, the basic lens equation. So the basic lens equation is 1 over the focal length equals 1 over the distance to the object. All right, so distance to the object would be the distance from the lens out to this button here we're trying to image, right? From the lens out to the button. And then the distance to the image, right? The distance to the image is the distance from the lens back to the image. Now, in this situation, one thing you'll notice in this drawing is that the button on the retina is upside down from the button out there. And that is in fact true. All of the images that you're processing, everything you're looking at right now, this video, on your retina is upside down from the way you perceive it. Not a terribly important piece. I mean, your brain deals with this. Your brain from day one began processing information like this and understands it, right? And as a matter of fact, your brain is so good at this, if we built some goggles for you, and this experiment has been run, if we built some goggles for you that flipped everything upside down, after a couple of weeks, your brain would adjust and you would perceive everything as right side up again. And then when you took the goggles off, everything would be back to being upside down, and after a few weeks your brain would figure it all out again and you'd see everything right side up again. All right, so right here, the basic lens equation. Next is what we call magnification. This M is just the magnification. And the magnification is just the height of the object, the height of the image, pardon me, divided by the height of the object, right? HI over HO. Well, in the case of this button, its height is now negative. And the reason we think of it as negative is because it's upside down. All right. The magnification is also minus the distance to the image divided by the distance to the object. Now, this is in no way close to scale. Nobody can see a button that's this close to their eyeball, right? I mean, you just can't. And so this is these are the basics of the optics of the eye. There are several things that go wrong with the eye that also go wrong with a lot of optical instruments and other remote sensing devices. Because when I say optical, I usually mean the frequency range that the human eye can see. But the near infrared and the near ultraviolet aren't all that different from the human, the systems that we use from that are not all that different from the human eye. So it's not until we get far away from the optical range that the systems we use to collect that data are dramatically different from the human eye. And in fact, a camera, a standard camera, is nothing other than a lens out here that you can adjust with either some film here or a CCD here, right? And so you're using the lens and you're moving the lens in and out to change the focal point, and you're changing the lens power, and you do all of that to focus back here on the film, right? And so you adjust when you're playing with the lens on a camera moving in and out, you're playing with this equation, right? Now our eyes, we play with F, right? And in a camera we play with DI. F is typically fixed unless you change out lenses. F is typically fixed, but we play with DI. With the eye, we don't play with DI. That's fixed, so we're playing with F. But in other ways, they're very similar, right? And you can have, and I have used cameras that are in the near infrared. I've not ever used a camera that's in the near ultraviolet, but you can construct such things. So there are things that go wrong. There's, myopia, a big problem for me when I was a teenager and on through college. My diopters were minus 6.5 back when I had surgery, correcting my in my 30s, correcting my vision to 2015. And since then, I've started doing the over 40 thing. I'm now getting some hyperopia, a little bit of farsightedness, and I still have creeping back in some nearsightedness. Okay, so that is the human eye. Back here, we'll talk more about what's going on back here in the next segment of this video presentation. And so, again, lens equation tells us how the eye behaves, and from there we looked a little bit about things that go wrong. All right, this is all for the visual spectrum, the optical spectrum we call it, and in a minute we'll talk more about that. And that's it for this segment.